All right, let's get this party started. Just checking. Audio's coming through, looking good. Then, yeah, we can get to the good stuff. So, welcome back to my little Elm exploration programming for fun and enlightenment. Today, we're going to actually start looking into starting the actual Tetris program. And from a functionality point of view, I have the rough goal to be able to render the initial grid for the Tetris game. But before we go into this, I just want to cover the basics of an Elm program again a bit and go into a bit, just use the opportunity that I can ramble without somebody stopping me to give a bit more context about why I'm doing this. So the reason for this is not so much that I think all programs should be written in Elm or it's the only web framework that there should be. It's just that programming in Elm is as the channel name indicates, it's just fun. It's the programming language I use in my spare time the most currently. And I think one of the reasons why it's so much fun is because it fosters a way of software engineering or constructing software that other programming languages don't foster that much. And the reason for that is I feel Elm is a programming language that was designed with humans in mind first, where other programming languages, especially the ones that are older, like 10 or 15 years, have a strong background in being optimized for the computers. Their main design goal is to bridge this gap between humans and computers, but mostly by exposing concepts of the computer, where Elm is a language that is trying to work mostly with concepts that are pure logical concepts that live more in the domain of logical problem solving, and then have these be understandable by the computer as well. We'll see a bit more what that means once we start coding. But as I said, before we do this, I'd like to look a bit more into the general application layout or principles of an Elm application. So last week we looked into the sample boilerplate application that I have with my hot code replacement setup, and went through this kind of line by line. And today I want to look at the larger concepts a bit more in general. So a few things that I think are worth pointing out about an Elm application, contrary to a regular program that you would write in Ruby or in C or Java, is that in Elm, the Elm application code doesn't really do anything. So that doesn't mean that the program doesn't, or the application, when I use it, doesn't do anything, but we don't have statements in Elm. Everything in Elm is an expression, it's an expression in the mathematical sense, that any number 5 is an expression, or 5 plus 3 is also an expression. And in the same way, the Elm app never does something in statements in other programming language are, for example, to print something on the screen or on the dev console. There are some debugging mechanisms in Elm as well to print something on the console, but it's only for debugging purpose. Everything that you do to have the program behave in the way that you want are never statements. It's all just a big tree of expressions, in tree in the sense an expression 5 plus 3 can be collapsed to one expression that's just 8, and then in a similar way, the entry point for our Elm program is the main program, and but then this is just an expression, the sandbox browser, and each of those components in it is an expression. Our actual update function is an expression, and the view function. And to understand a bit better how we still get something that the computer to behave like the way we want it. We look a bit more into these components again on a more abstract level before we jump into coding directly. So as I said, we cannot change anything, but this is also liberating, and that's why it's programming in Elm is so much fun also to me, is we don't have to change anything. So everything, all the error classes that can happen that are related to statements just don't exist in Elm because we don't have statements. How does it still do something useful? So we went last episode over how Elm consists of these basic three elements. Our model, which is kind of this global state of our application, which is managed by the Elm runtime engine. Then we have the view function, which basically takes the instance of the model, the state of the application, and calculates a DOM tree based on this to give a visual representation of this. And this visual representation might contain UI elements like buttons or input elements, and interacting with those creates messages that we send again to the runtime engine, and the runtime engine uses our update function that we supply to take the old model state, the messages received, to create a new one. So how does it syntactically look? Let's look at our model or our model type first, because Elm is also a strictly typed language. We cannot just throw an arbitrary JavaScript object or something, key value pairs in there. We have to define actually what our model state is, or our application state. And in the example we started to look at last week, and that we are going to base our Tetris application on, like the example code has a model that has two fields, a left and a right, and both are ints. And in our initial state for the application, both these counters are going to be initialized with 0. Then the view function, this gives another opportunity to look, a bit at the Elm syntax again. So this is a function declaration. The first line is the function signature, where we have the function name, the function parameters, and the function's return type. So this declares the types of the parameters and the return type, and in the next line we repeat the function name again to basically link those two together, and we give names to the actual parameters. So here that's why it's local, lowercase are variable names, and then in this let in, like in is what we define an in is the return value of that function, and in this let block between the let and the in we can declare local variables. So here, and we use the button function to render a button element, and the button element is also just a function which takes the function call. Contrary to other languages, we don't need parentheses. We just give the parameters to the function call directly after specifying the function name. The first element is a list of attributes, and the second element is a list of child elements for our button. So here for our as child element for our button, we want to display a text node. This text node is created here by using the text function and a string. And also something that Elm doesn't have is implicit conversion between types, or auto-boxing, how it's called in Java, or auto-unboxing. So if we in our model.left, we have an integer value, but we want to use it as a string. So we have to explicitly use the from in function that comes with Elm, obviously. And I have a typo in here because an onClick is actually missing a parameter, but we'll look into this later. So the view function is the function, as I said, that turns our model into something visible. And yeah, this thing that was missing in the onClick on the last slide was basically what happens on click. So what I would have put there is the left. So instead of just saying onClick, it should say onClick left. And this left refers to one of the variants of our message type. it's a type that we define ourselves, because obviously the Elm runtime system cannot know about all the possible events that happen in our application. So we can define it ourselves, and we define it in terms of an algebraic data type. And that sounds very scary, but it's really only basically a list of mutually exclusive values that a variable of this type can have. So in this sense, it means the messages that can exist in our system are either a left or a right message. And so just to give another example and go through the exercise of looking at Elm function, here's an example function that we don't use in our application, but just to show you some basic control flow elements in Elm. So we have a function that is called left is small, that takes in parameter int and returns a value of our type message here. So our actual parameter name is I, and so we don't declare any local variables. That's why you don't see the let in block here. It's just basically what would be in the in block. And it's, as I also mentioned last week already, we don't need explicit return statements, because each function in Elm has to return exactly one value or one expression. So it has to be and the good thing about this is, like in JavaScript or in Ruby, you can forget the return statement and then it will return null or nil. And that's most of the time is like a very annoying bug to find. So in Elm, because we have the certainty that each function has to return a value, the compiler can use this convention or this assertion to warn us if we forget this. For example, so this function looks if I is smaller than 0, then it will return the left variant for the message, otherwise it will return right. And if we would forget to specify the else branch, then the compiler would yell at us and make us implement it. The program won't compile until we also specified the else case. Cool. So the last missing piece for our small test program to be complete is the update function. So the update function basically specifies what happens to our world state, application state, model. Those are all kind of interchangeably used expressions for what the model means. What happens if our application receives a message of a certain type, and how we turn the old model into the next model. So, and it's again plain old Elm function. Just this time we receive 2 parameters, and that's a bit uncommon for or hard to or surprising for people who come from other languages, is that we don't have this clear separation or this explicit separation by characters from what's the return and what are the parameters. But it's like the last, what is the type after the last parameter, after the last arrow, is always the type of the return value. Each function can only have the one return value, so we know implicitly that each other type separated by arrows defines the type of a parameter. And that's why we have, in the next line, we have 2 words or identifiers for our actual parameters again. And again, because this time they are variables, they start with lowercase letters. And similar to the if statement, the compiler makes sure that if we have a case statement, that we handle each variant of that type explicitly. So in this case, as I said, like message has 2 variants, left and right. And for each case, we return a different new model. And this is the syntax to update a single field of a model. So that means we create a copy of the old model and we update the field that is called left with the value that's on the right side of the equal sign. So in our case, if we receive the model left, we increase our left counter by 1. And if we receive the message right, then we increase the model right by 1. Cool. Nothing complicated here. So just to bring it back where we started, I said an Elm application doesn't really do anything. So if you just go through your head what you saw so far. None of those functions actually print something or adds something. Like it's really pure functions, like in the mathematical sense, like we learned it in school. Like one thing goes in, or multiple things go in, and another thing comes out. But we're not changing, we're not modifying memory, we're not modifying the screen or anything. It's just straightforward transformations or calculations based on the model state and the messages. So if you might ask, like, if we are not doing the thing, who is doing the thing? And the answer is, if we compile our Elm program into a JavaScript file, this JavaScript file does not only contain our application code, it also contains the Elm runtime. So it's a bit like the JVM, which is this machine that basically executes our code. And the responsibilities of the Elm runtime are that it stores a reference to the current model for us. We are just supplying it with the initial state, but it holds the reference of the current state for us. Then it calculates the view, like the DOM nodes and so on and so forth, based on that model for us, based on our view function. And then it listens to messages that are getting emitted by our buttons, like our interactive UI elements. And then it uses our update function again to calculate the new state of the UI. So just to see this all in one big diagram, like if we start here at the top, and the current model will be what we give the Elm program as init function. The runtime uses the view function to calculate the new DOM. We get a button with some on-click event listener attached to it. And if we click the left button, then the runtime receives the message left. It calculates the next step for us. Whenever we never call the update function ourselves. We also never call the view function ourselves. Like, this whole loop is controlled by the Elm runtime environment, but it's outside our application. We never have to specify when to call. It's similar with React or Angular, where you also you specify the render functions for your components, but you never actually call them yourself. So yes, that's the big picture of the application. And I think with that we have enough context to actually start coding on our Tetris clone. So to do this, I will jump into the console, and I will not build on what we explored last week. I just quickly start over to catch up people who haven't viewed this. I will create a recursive copy from my boilerplate setup, which lives in this Elm Nano example repository that I also have on GitHub. You can find a link for that on my blog. It's called Hot Elm because it does hot code reloading. And I copy this into a new folder called Tetris, and we are going to change into this folder. I have a second console here to the right, where I also will change in this folder just to have our continuous watcher that continuously builds our project going on. So here I would call the build script that we looked at last week, and luckily the default state of the program doesn't contain any errors. So if we open the index HTML, I increase the font size here a bit, then we see we have the behavior that we looked at a bit in the slides already. Cool. So that's a good start. We can have a look at what's actually in this boilerplate. There's some Elm stuff that we don't have to be concerned with. That's stuff that gets maintained by the Elm command. We have a few assets, a styles CSS. The loader CSS is just that thing that keeps reloading our JavaScript file after it gets compiled, and the real magic happens in the source folder. And as you can see, there's really not a lot, just the main Elm. So I will open this right away in my code editor, which in my case is Vim. Cool, I think the font size is good. And you see this is not one-to-one lining up with what I showed in the slides. There's also something here called subscriptions, which I will go into detail about in a later episode. And there's something else here, this command message. Our init is not really just a model, it's a tuple of command and message. And if we look at the update function, we also see that it does not just return a model, but a command and a message. But again, I will keep this for a later episode. For now, you can just ignore it and pretend it's not there, because it's not really significant for what we're doing today. So obviously, the model with a left and a right counter is not really suited for us. We want something for our Tetris. And at this point, like, this is directly where I start to work differently in Elm programs than I would have, at least. Like, I'm using a lot of the techniques I learned through Elm in my day-to-day programming, in my day job as well. But I have the feeling that I naturally attack problems differently in Elm than I would in other languages. So if you think about how do I want to represent a board in JavaScript, people usually jump directly to two-dimensional arrays and think about what to store there in their zeros or ones or characters. And in Elm, we start differently usually. Like, we think about types first, and instead of trying to use what's there as much as possible in terms of what the computer gives us, we try to create only what's necessary. So let's start right about, like, I still would argue, like, the minimal thing to start with for Tetris is to have this board. So I will just introduce a new type, and I will call it board. And it will, for now, well, let's like, it doesn't have to be an algebraic data type, I think, because we don't have variants of a board right now. So it will just be an alias for something else. And I would argue the way I think about a board is that it's a list of rows. So I will just jot that down, list of row. So that's good. And we will incorporate this into our model, into our application state. So we say board of type board. Cool. Let's save this and let's look at what Elm has to say about this. And this, again, like, this is very dogmatic or typical for how I develop Elm. I just add what I want to add, and then I let the compiler basically guide me about what's missing. Like in other, like in Ruby, we would probably have to do something like test-driven development, where I would write that I want to access this board, and then then when we run this test, then Ruby will run over this property and tell us it doesn't exist or is undefined. But as you can see, like it's hard to beat in terms of feedback time if this step can be taken by the very fast Elm compiler. So it cannot find a row type. That's also fine. So let's say type row equals, okay, let's just say for now we just want to have an empty board. So an empty board is a list of empty rows. So we just define that. And now it tells us something is off with the body of the init definition. This body is a tuple of but it should be a tuple of model and this. So what it's telling us is that this first part here, the left, right, the thing that has left and right, is not matching the type model that it says it should return. So let's look at line 43. And it's complaining rightfully because up here in 29, we said, like, our model has a field board, but in line 43, when we initialize it, we only initialize it with a left and a right field. So let's add the board here, and we can instantiate a list with the squared brackets like in other languages as well. And we just put in one empty row for now, just to please Elm. And now it compiles again, so that's great. And now we can also, I would go right away and remove all the boilerplate code. So we don't need a left counter, we don't need a right counter. We can collapse this into one row. We can remove this from here. And we save it. And then again, the compiler will tell us all the places, obviously, where we are still accessing those fields or trying to modify them. So we have to remove this as well. Line 59. For now, I will just return the old model. So that means when we receive a message left or right, instead of creating a new copy of model with some altered state, we just return the old state. That should be fine. And then we see in line 85, we are still accessing the left property of the model. So let's go there as well. So instead of saying model left, we'll just to have a minimal change, I will just dump a 0 in here. We will look at the board representation in a minute. So for now, let's just get it to compile again. Changing, I mean, I can just throw away these buttons because we don't need them anyway. Like this. Cool, look mom, no server. And yeah, maybe we just leave it like this. Maybe we just look at actually rendering the board right now. So to render the board, we have to modify the view function. So like we have this text here, but we also want to have something beneath this, the board view. Let's call it board view, and we pass in the board, model.board. So board view is obviously a function that doesn't exist. So we write a new one, and it receives one parameter, a board, and it returns HTML message. So HTML message is it's not two types, it's one type with a type parameter. So whatever follows after the space here is a type parameter to the HTML type. And that means this function generates HTML, which is able to emit messages of the type that we specify here. So in our case, it's our message type, obviously. And it's the Elm comes with the HTML type, which comes from the Elm SDK, comes with the type parameter because obviously the runtime does not know about our concrete message type yet. That's why it has this placeholder, sorry. Cool. So let's again complete here the function body. So I think we want to I want to use SVGs to paint the board actually, and my idea is I don't want to paint grid lines or something. I'm just going to always paint all the squares of all the rows, and if the field is empty, I'm just going to take a slightly different color than the background color of the HTML page, and I'll leave a small gutter space between those squares, and then they will by negative space create grid lines. So let's look at how to do SVG in Elm. I'm just going to search for Elm SVG, and usually that brings me, my Elm history is, my Google history is obviously tainted with Elm searches, so I cannot guarantee it will be the first hit for you as well, but usually this leads to success. And this is a typical page of the Elm documentation. I really love the documentation of the core modules that come with Elm, but also for external library, the documentation is standardized in this format and available through Elm package. And so let's just copy this example because, oh well, or we can talk about imports a bit as well. No, actually, let's not copy this example because as you can see, the names that you see in those examples, you always can assume the example is complete when it comes to import statements. So if we import a package like this, import svg exposing, whatever is in parentheses after the exposing specifies the concrete functions we want to start using from that packet. And as you can see, here's ... which just means import it all. And what you can also see, so that means basically each time you see a black string here in this example, this is a function that comes from either of those packages. And as you see, there are some functions that have really generic names like width and x. And once you have imported those functions on the top level, they basically become unavailable as local variable names because Elm is also very particular about this and will be like, yeah, I don't know which one to use, so better choose. So that's why we are going to do in explicit, or I don't know what's the proper name for this type, but we are definitely not going to use this all-in method. We'll just start by importing svg, and then we have to prefix all those functions eventually with svg. So let's just to be syntactically correct, let's just render a diff for now, an empty diff. So just that we start with the compiling state here. This is all good. And then we'll import svg. Cool. Okay, you are trying to import svg, but I checked the dependencies and I cannot find it. That's what it's saying. Maybe it's a typo. But it's also, and I love this, the compiler messages of the Elm compiler are the best that I have seen in any of the programming languages I have worked with so far. So it says like, if it's not a typo, check the dependencies and sources, source directories, blah, blah, blah. So yes, obviously we are missing that to declare this dependency. Cool. So I'm going to abort my build step because I have to modify our dependencies. And one way to do this is to modify the Elm JSON manually. But another way is to just install the package via the Elm command itself. And I always forget the exact syntax for that, but luckily I have enough examples in my bash history, so we can just look it up. But what we want to look at is the name of the package, which is dash separated in this namespace notation. So it's probably elm-svg that we're looking for. And I'm just going to try to wing it and just be like elm install svg. And it says like, oh, I'm having trouble with this argument. Oh, so actually I was lying. It's not hyphen separated. It's actually slash separated. So it tells me, yeah, you probably want one of those. And of course it's right. The computer's always right. I want this. And it tells me, here's my plan. Like it doesn't just do something and maybe messes up your setup. It's really very defensive. Says like, oh yeah, I see you want to update, you want to add this to your project. Should I update the JSON accordingly? And obviously that's what we want. We are going to restart our build script, compiled without errors. So let's open our index.html again. Yeah, it's working again. So now, after importing svg, we have access to all those great functions like svg, width, rect, whatnot. So I say, let's be a bit more, oh no, we are going just to use a named imports. Like we are going to be very explicit about where we're using the functions from. For now, we can still refactor it later if it gets too annoying. So instead of diff, we want to have an svg. And again, svg, like other DOM element functions, receive two parameters, one for the attributes, one for the child elements. So what are they proposing here? This looks all very sensible. Yeah, we're just going to copy this whole tree. Boom. Fix the indentation a bit. So as you can see, like we're missing the closing bracket. Like this, these 4 lines are the attributes list. And then for our children list, you want to have an element with 1 rectangular in it, a 1 element list. So for now, I know, like, yeah, let's be explicit, because as I said, like I am pretty sure I will need width and height and so on as identifiers for local variables later. So let's be extra cautious here and use explicit namespace SVG, and even the SVG function comes from that package. So, and these are actually attributes. So if these are not, I just know that, but you would find out eventually, just a shortcut, like that that's a typical way to package HTML elements in, or functions for elements in Elm, is that the attributes here live in a separate import. So I know already we have to import this as well. But what I also know is I don't want to write svg.attributes.x, svg.attributes.y. So we are going to take a little shortcut, just also to use the opportunity to learn a bit about the import statement. We can write as svg attributes. I just create a shortcut SA to address those. And now we can write SA. Oh, that was actually wrong. SA dot. Okay, cool. So hopefully this compiles. Let's check what the browser is telling us. No, I cannot find an SVG width variable. That's correct, because this is also an attribute actually. So like all the attributes should be imported from the SVG attributes package. Did I not save? I did not. And we have a black rectangular. We can inspect this just to look at a bit how SVG is represented in the browser. It's a nearly direct translation from what we passed in as attributes into HTML attributes. Cool. So basically we know how to draw a rectangular. And my goal would be now to draw a lot of rectangles to eventually make up the playing board for Tetris. I don't want rounded corners, so let's remove those. Poof, that's nice. And let's say the background of our playing field should also probably not be black, more something like a light gray. So I will look here. What is probably color sounds very good. Takes a string and generates an attribute. So our rect has a color. Let's just be lazy and say gray. Check the output. That did not work. No, it's probably background or fill color or something like this. Let's look again. Search fill. Yeah, it's the plain SVG stuff is not documented. Like it's not a documented to learn SVG. So like we can literally go SVG or Mozilla fill, and we see we directly And the fill attribute has two different meanings, shapes and text, defines the color used to paint the element. So that sounds a lot like what we want. So my bad here. Try gray again. Cool. All right, that's a good start, I would say. And as I said, like my understanding of a Tetris board consists of multiple rows, so the board should obviously be not just one field. So, but I want to have a list of rows, so I also create a row view. And again, like I can really, very similar to how I would think about test-driven development. Maybe it's type-driven development. I'm just making stuff up as I go. I really write down what I want to do in terms of types. So the row view should receive a row, obviously, and again, return HTML message. Cool, so it receives the row. And I would argue it's probably a good idea to also create a function for a single field. Let's say, call one of those boxes a field. So we will receive we don't have a field defined yet. So we don't actually need or maybe actually we do need a parameter to tell us which column this field is in. Does it make sense? Well, let's start without. Let's be very naive. And we'll just copy our code for the rectangle. Oh, actually, of course, we will only move our code for the single rectangle and not for the whole SVG, because the SVG is actually going to host all of our SVG elements. And yeah, maybe here we start direct. So I will just leave this empty for now. So just as it compared. So our SVG is empty. And like to get in a compiling state, I have to obviously complete the function declarations that I did here. The row field should be complete because an SVG rect is an HTML message. So we're cool here, but we have to do something for a row. And a row is actually consists of multiple, sorry, that's the wrong syntax. It's a row will not contain only one field, or the HTML for one field, but for multiple. So we have to actually return a list of HTML elements. So I'm pretty sure, I have a feeling I will want a few local variables that's why I'm creating a let in statement here. And I will just create a constant here, local constant or variable for the board width, for how many columns we have. Like, let's say we have 11 columns. And so what I want here to be in here, basically, I want a row field, and so on, 10 times or 11 times with that, with the board width. But obviously, I don't want to write this out, but I want to somehow generate this expression from the knowledge that I can just 11 times repeat the result of the row field function. So something else that is missing from Elm are for loops, because to have a for loop, I need to increment a variable. So incrementing a variable means changing a variable. And as I stated before, in Elm, we don't have statements to change variable. So the way that is done usually in functional programming language is to use the map function, which is basically can transform one array with the use of a transformation function into a different array of the same length. So in Elm, like we have a specific function called list range, which I can use to create a list of integers between two values, here between 1 and 11 in this case. So I will call will create a range that I call columns locally between 1 and 11. And then we will use the map function. Well, it's actually also the list map function. And I will use, well, I will actually introduce a parameter column to our row field function. Or actually, I consequently should call this our row field makes no sense. I wanted field view. So field view is our transformation functions for our map, and we will map over the number of the columns. Cool. Let's see what I missed. Let the compiler help us. I cannot find an integer that type. That's correct because it's just called int. Oh, and it's compiling. So that is fantastic. And now, of course, we want to use the row views here in our board view. So we'll do something similar again. We want to have the board height. Let's say 20. And we want to calculate the row views, which are again a list.map over board.rows with a helping function or transformation function, row view. And then we will replace this empty list of child elements for our SVG with our row views variable. I should rename this here to views because it's multiple. Cool. And row views, the second argument to SVG is not what I expected. Row views value is a list of HTML. Okay. Yes, because each of the rows produces a list of elements. So if we produce one of those for each of the rows, we get a list of lists. So we want to concatenate them into one big list. So we use list.concat. And to make sure we are passing in the right value, I'm using parentheses here. And board.rows. This is not a robot. So yeah, true. Current. Let's look at our type definition for a board. Type alias. Whoops. We said a board is a list of rows, so it doesn't have fields or anything. But maybe we change this now because I really like how this read here, that I can access the rows of the board, and I have the feeling I will have to add more fields to that later. Cool. So rows is a list of row. Cool. Is my sound still going strong? Yes. Good. All good. Cool. We also have to change, of course, how we initialize our board then. So we'll say board is this. It's an equals and another closing bracket here. Something is off. Board row. Yeah, it's rows. cool. So this compiles again. It looks a bit like it didn't work, but if we inspect the SVG, then we see we actually have the 11 rectangulars. They're all just at the same position. So let's change this. In our field view, we get already the integer, which indicates at which column we are. So we are going to change the X position. So as I told you before, like the X function expects a string, but of course, when we start calculating things, we want to calculate based on integers. So, or let's just make the calculation first. Let's say we want our rect to be 10 units wide, and we want to have a 1 unit spacer in between. So we can just say like column times 11. But since we want to, since we have to convert this to a string, we will call from int with that value. And so this will technically work. It's probably still indistinguishable, the result, because it's just too big. Or we will make the width hard-coded to 10 here. Okay, and that looks, and the height for as well. And now it looks much more like what we want it to look. So another Elm syntax trick I want to show you is that nesting these parentheses gets out of hand quite quickly. And we can write this more in a more like pipeline style. And we can use this operator for that, which is basically saying everything that comes after this is part of one parameter, or what would be in one pair of parentheses. So we can repeat this trick, and then this reads a lot nicer, because now we can really read it from the right to the left to be like, oh yeah, column times convert this into a string, and then we pass this into the X function. Cool. So we have one empty row. We have one row of gray squares. That's great. But actually, we want to have... so this is obviously not a board yet, but just one row. So what we want to do is actually base our rendering of the list of rows. And we only have one row in our model, so that's good. But let's just say we want to have a second row in there. Empty row. And this previous calculation, or the definition of board height, is actually not necessary, because we have a list of rows, so we know how many rows our board has. But row view only gets the content of the row currently, and not the row. We don't know the which number of the row is. So we have to have the row number as well. So row number, and obviously there's something missing, but just as an exercise, let's have the compiler tell us what's missing. It tells us the first argument to concat is not what I expected. It's, oh yeah, that's a nice way to think about it, because actually, like, it gives a bit more insight or an opportunity to explain why argument lists are written so weirdly in Elm, opposed to other languages. So as you see, or not, this map call it's referring to here, when it says this map call produces a list of, and this looks like a function signature, and it is a function signature. So that means what's here in the parentheses is a list of functions, and each of these functions expects a row and returns a list of HTML elements. So why is that? Because we're passing in row view into map. And row view receives 2 parameters. But by mapping takes like basically the elements of this array and passes it for each of the elements, passes this into this function. And this function, like we are only filling the first parameter. So we are producing, by mapping a function that takes 2 parameter and only filling 1, we are producing an array that still needs 1 parameter. And that's exactly what the Elm compiler is telling us here. And that's correct because it's as it says, like it's not enough to just pass in the row. We also need to pass in the index of the row. And for that, there's a special function in the list package. I'm just going to look up the core, going to go to the list, and there's a function that's called map with, or indexed map, I think, something with index, yeah, indexed map. And here again, a good exercise to look at stereotype signatures in Elm. So maybe we look at map before, apply a function on every element in the array. Like that's pretty common as in plain old JavaScript as well. And the signature reads as this: map is a function that takes a function that turns an A into a B. It takes also an array of A's, and it produces an array of B's. So A and B are type variables because map will work with no matter what types. And an indexed map like also takes an array of A's and makes an array of B's, but the transformation function takes not just an A to produce a B, but also an integer. And this integer is the index of the element in the array that we put in. So that's exactly what we want for our row view. So we can, instead of using the plain old map, we use an indexed map. So let's see what the compiler has to tell about this. Nothing. So that's great. That means it works. So now we are receiving the row number here. But the question is, why do we still only see one row, right? And the reason for that is because we are not telling the field view in which row the specific field is. So we need to tell us we're going to pass in another number, which is the row. And we are going to do a similar calculation than we did here. We want something that was a string, an int for sure. And we want to have the same dimension, like 10 height, 1 pixel or 1 unit space between. So we are saying row times 11. And now something is off with the body of row view. This map call produces so it's the same phenomenon again. Like we're doing a map and we're giving it a function that takes 2 elements, two arguments, but we're only filling 1. So field view. So now we could say like, it's probably indexed map, but this is wrong, because if we do an indexed map, then we are passing in the column number again, which is not what we want. What we actually want is we want to pass in the row number. And now comes the beauty of these functional programming languages. Like we are calling field view, which takes 2 parameters, but we're passing in only 1. So how can this possibly work? Like this should not be a valid call, but I mean, we're also not really calling it. We are passing this function into the map function. So this is called partial binding. And what this means is we are creating a function that has already one of the placeholders is taken with the first parameter is taken basically. Like we could also actually create a local variable that makes it maybe more concrete. Field view for row, and we are going to field view partially bind this to the it's actually row number. Oops, row number. That's what I referred it to above. So here we can now remove this in the parentheses and just call this variable. So in this variable, we now have stored a reference to a function that has one of the two parameters bound. So it's only a function that takes one number and produces an HTML message. And that again matches our requirement to pass it into the map. And we have our 2 rows. So that means we can also automate the creation of the empty board. Let's remove this and call it empty board. I could now just go here, empty board equals boom. So this should yield exactly the same result. I'm reloading, boom, still looks the same, no errors, is fun. But obviously I don't want to write it out. I want to have somewhere coming from a board height number 20. And we're going to create a little function, make empty row, that takes a parameter that we are not going to use and returns an empty row, because this allows us to do a list.map with make empty row. And because I'm too lazy to use parentheses, so I just find it nicer to read, I can say again list.range from 1 to board height. Boom. I'm not sure exactly, or what did I say? What's the board height? 20? That doesn't look like 20 to me. Or I think that's basically because the view box of the SVG is not correctly calculated. Like we see, like, yeah, this is still good, still good, still good. And then this is also still good. And then, oh yeah, here's something outside of the viewable area. That's some SVG view box. Like if we just extend this to 200 and this 200, then it looks a lot better. So, but that's more browser fiddling or SVG fiddling than really Elm fiddling. And yeah, it's already 8:05, so we're over an hour. I'm pretty happy with how far we come. Actually, it took a little more time than I expected it to take. Oh, my MacBook also wants to turn off. But yeah, I think that's a good position or state to stop looking into. So thanks for staying with me or watching this video. And next week, we're going to start looking at how to model the pieces eventually. So looking forward to this. Have a great day and see you next time.